Bennett, and for my practical online final, I chose to do the lab about the properties of metals using pennies. So the purpose of this lab is to learn more about the properties of metals, while also correlating it with a real-life issue. So the materials I need for this lab are vinegar, salt, a couple of measuring cups. This one is 1/4 cup, and this one is 1 teaspoon. 30 pennies, I'm not sure if you can tell on camera, but they're all there. 2 screws, both steel. A glass bowl with which to contain our solution, and a spoon with which to stir it. A timer, and a colander. Colander will come into play a bit later, and it's not really necessary, but it does help. So as for safety procedures in this lab, I'm wearing goggles because, say if this vinegar were to splash into my eyes, probably would sting a bit, and it's never a good idea to get chemicals on contact with your skin, so that's why I'm wearing the gloves, also to minimize contamination of the solution. So to start off here, I'm going to pour 1/4 cup of vinegar into the bowl. Okay, so now I'm going to prepare the solution. So what I'll need is 1/4 cup of vinegar, being careful not to spill here. And I'm going to mix that with 1 teaspoon of salt. Let's move this out of the way. And this will create our solution to do some stuff to these pennies. Now what I'm going to do is stir this until all of the salt has combined with the vinegar. And as you can hopefully see here, the salt has mostly combined with the vinegar, and that means we're ready to move on to our next step. And that is submerging 1 penny here, halfway in it, for 20 seconds to see what happens. And what should happen here is the copper oxide on the outside of this penny should dissociate back into the ions copper and oxide? Yeah, oxide. So I'm going to set the timer, and I'm going to stick it in. So as you can hopefully see now, half of this penny has become a lot more shiny and clear, and the other half is still a bit dull. Well, let's see what happens when we put the rest of the pennies in for 5 minutes. Okay, so it's been 5 minutes, these pennies have been soaking, so now it's time to redistribute them a little bit. So first off, we're going to put half of them, without rinsing them in water, onto this paper towel here. And now we're going to go rinse the other half of them, so that there's no vinegar and salt solution left. That's what we needed the colander for. Alright. Okay, so now we have our pennies set up into two different groups. This group has the vinegar and salt solution still left on them, and this group has been washed off. It seems we've lost one of our pennies, but that shouldn't affect us too much. So now we're going to let these sit for an hour and see what visible changes happen on them. But I'm sure you can see right now, one observation I've made is these appear to be a lot shinier and cleaner than when we first had them. So, well, let's let them sit for an hour. Okay, so here we are an hour later. Managed to find the missing penny because it was just stacked on one of them. So let's look first at the pennies that we did not rinse. So as you may be able to tell now, they look a lot duller. And that's a good thing, because that's exactly what we were hoping for. Now, as for the ones we didn't rinse, not all of them, but a few of them have a green tinge to them. And that is also the result we were looking for, but I'm going to leave them overnight so that we can see if any more happens to them. And I will explain more about them when we get to that point. But for now, let's move on to the next part of our experiment. Here are the pennies 1 day later. As you might be able to tell, not much has really changed from the initial check-in, but the pennies I didn't rinse are slightly duller, and some of the ones I did have a greenish coating on them. This is called verdigris, a mostly harmless and often helpful outer layer, commonly referred to as a patina. Patinas protect the substances they coat, and verdigris is a particularly famous one. This is because, since the Statue of Liberty is made of copper, it has a coating of verdigris that gives it its distinctive greenish-blue color. Okay, so for the final part of our experiment, we're going to see if we can copper plate these screws. So these screws are made of steel, and steel is composed of iron. So what we're expecting to happen here is the iron in these screws will react with the acetic acid in the vinegar, and as such the iron will be removed, and the leftover copper ions that are still in here, the oxygen escaped as oxygen gas. We're going to hope that the copper ions plate these nails. And just like with the last experiment, we're going to put one of these half in and one of these all the way in. So let's do that now. And we're going to leave these to set for 10 minutes. The stainless steel screws I used in this experiment didn't get copper plated even after an extra hour in the solution. This is likely because the lab called for pure steel nails or screws composed mainly of iron, which I was unable to find.
Thankfully, I was able to test some other metal objects I found in the garage to much greater results. The small bolt you can see in the middle here reacted the most violently. It bubbled up and turned a dull brown almost immediately, which means that the reaction it had with the acetic acid solution was instantaneous. The screws from earlier didn't bubble at all, which means that no hydrogen was released and the reaction failed. I got even better results with the rusty wrench I used here, since it was composed mainly of iron oxide on the outside. This means that a similar case to the pennies occurred. The iron oxide broke up into iron and oxide ions, and that made space for the copper to plate it on the outside. Here is a picture of the metal objects after their bath in the vinegar solution. You might not be able to tell, but the two screws in the very middle soaked for about an hour and 15 minutes, whereas the other metal objects only needed 10 minutes. As well, I put a couple of the screws that I didn't use on the ends for comparison, which makes it plain to see that there was hardly any copper plating on the ones that did soak. The lab that I carried out most closely relates to the issue of water pollution. Sure, I used vinegar, an acidic substance, in lieu of water, but the basic concept still stands. Water is commonly known as the universal solvent because of its tendency to dissolve most things and create solutions. This means that it can combine with a great many things, such as metals and other pollutants. Say, for example, I left an oxidized penny in salt water rather than in my vinegar salt solution. This would be a similar instance to what I did in the lab. I'd be combining the copper oxide on the penny with the salt water, which acts as a saline solution. The activity series states that the copper ions in the copper oxide would be replaced with the sodium ions from the salt, right? Well, what if there wasn't any salt whatsoever? Then the copper oxide would simply be dissociated into its pure ions, Cu2+ and O-, and the O- ions would likely link up and be released as bubbles of oxygen gas. But that still means that the pure copper would be in the water, polluting it. This is backed up by a study of microbiology that I found. Although the article itself speaks in a lot of technical jargon, after I managed to cut through it, I was able to prove my hypothesis. With increasing amounts of salt, spare copper ions decreased along with water pollution. Essentially, more salt means more replacement reactions, and fewer harmful copper ions in water. And this basic concept can apply to other metals too. However, that still means that metal in fresh water would pollute it, as there is no salt in fresh water to perform these reactions. This is especially a problem since metal ends up in fresh water fairly frequently, such as when freshwater boats that are composed of metal corrode over time. This is due to a reaction in which water dissolves metal compounds into ions and takes these ions from the boats. This is even something that can occur in our own homes, like when old pipes need to be replaced due to corrosion being bad enough that it directly affects water in the home. Polluted water can be treated to remove metals and other contaminants, but that only accounts for some fresh water, not all of it. And what about ocean water, which naturally has a lot of metal in it from ships, sunken or otherwise? Well, sadly, not very many people seem to care about the issue of water pollution. However, I did manage to find one article about how synthetic coral might be able to remove toxic metal ions from the ocean. The problem with this is that that article was written in 2015, and I couldn't really find any other interest in such a project, simply because ocean water isn't used as drinking water. But that doesn't mean it isn't important to consider the consequences at hand. Since metal is so susceptible to dissociation in water, and there is already so much metal in the seas from wreckage and garbage, there is a good chance that given time, our oceans will become entirely polluted. And the same thing will happen with our rivers, since so many fishing boats and ferries populate them. When that happens, many ecosystems on Earth will be disrupted, and life on Earth will be negatively affected in a big way. Metal polluting our water, oceanic or otherwise, is a big-ticket issue that seems to fly under the radar when we talk about pollution, simply because air pollution and fossil fuels are so much more widely known. But it could prove to be just as big of a threat if we don't start paying attention to it. So, what can we do about this problem? Well, as I mentioned, processing out metal in water treatment plants is great, as is this idea of synthetic coral, but we need to be doing more than that. One other way we can stem the flow of pollution in our oceans is by participating in beach cleanups. Although people seem to commonly toss plastic garbage on beaches, there is still a good deal of metal garbage found on beaches, like bottle caps, cans, and metal food trays. Especially here in California, where people come from all over to visit the beach, we need to do our part. I've included a link to some local beach cleanups in the description, and I myself am planning on volunteering once it is safe again to do so. Finally, just being cognizant of how pollution works and informing others about it can help to get more people to act against it. Information is powerful, and the spread of ideas helps to put them in motion.